Good afternoon, ladies and gentlemen. My name is Fan Dang from Tsinghua University. Today, on behalf of these authors from these universities and companies, I'm really glad to introduce this work, Understanding Fileless Attacks on Linux-based IoT Devices with HoneyCloud. The term Internet of Things, or IoT, was first coined in MIT's Auto ID lab in 1999, targeting at connecting everything using RFID technology. 20 years later, we have IoT devices everywhere. We use IoT devices to sense environmental data, control equipment, monitor the buildings, and so on. According to the report, The State of IoT Security from Gematto, there will be 20 billion IoT devices in 2023. According to this report, which can be obtained from their official website, almost 80% of companies ask the government to provide more robust guidelines on IoT security. Almost half of businesses are not able to detect if any of their IoT devices suffers a breach. Also, consumers are not satisfied with the efforts of the IoT industry. 62% of them believe that the security needs to improve. So what can we do? Our answer is honeypots. A honeypot is a computer security mechanism set to detect, deflect, or in some manner counteract attempts at unauthorized use of information systems. It is a computer system intended to mimic likely targets of cyber attacks. It can be used to gain information about how cyber criminals operate. We believe that if we can turn an IoT device into a honeypot, it has the highest fidelity, and it is capable of capturing every single attack. And therefore, we believe the hardware honeypot is the most directive and effective tool to understand attacks against IoT devices. So we first built a hardware honeypot. This is a photo of one of the honeypots. There are two parts. The left half is a remote control power adapter, and the right half is the hardware honeypot itself. This diagram shows the details. The upper component is the honeypot itself, which is composed of three parts. First, the basic hardware, including the network interface card, the RAM, and the CPU. Second, the OpenWRT operating system. And third, the services for tracking attackers. And in this implementation, we use SSH and Telnet services. The SSH service is provided by Dropbear, and the Telnet is provided by BusyBox. Dropbear and BusyBox are two very popular utilities in embedded systems. The lower component is the remote control power adapter, or we call it RCPA. RCPA is very crucial to this system because if our hardware honeypot is unavailable, we have to reboot it. In case that we cannot log in to reboot it, we have to use an external component to control the power of the hardware honeypot. The RCPA is composed of an Arduino, a power relay, and an Ethernet module. Once we send a restart message to it, the Arduino controls the power relay to power down the honeypot and then power it up. Beside of Raspberry Pi, we also use other devices as honeypots. The devices include Netgear and Linksys wireless routers and BeagleBone, a single-board computer. They have different CPU architectures. We place them in 4 cities in the USA and China. Although the prices are not too high, we have to pay the internet access fee for every single device. And the lowest price is as high as $30 per month. That is not cheap. So we wonder if we could put everything in the cloud, because everyone knows that the public cloud is really cheap. So we built the system. And in this diagram, the software honeypot is located in the red frame. Now, let's take a closer look at it. We use Cameo to emulate the IoT device. The operating system is still OpenWRT. Inside QEMU, we set up two components, High Fidelity Maintainer and Shell Interceptor. The High Fidelity Maintainer is responsible for making the software honeypot more like the real one, and the Shell Interceptor is responsible for recording everything that the attacker inputs. Let's first talk about how to achieve high fidelity. We use three methods to do so. First, we try to customize proper QEMU configurations. We set CPU architecture and memory size according to the device we would like to emulate. Second, we also forge the CPU info file to mask sensitive system information. And third, based on the observations that some public clouds will block some attacks, we also change the providers during the deployment. And of course, we change the IP addresses of the honeypots periodically. We collect CPU usage, process list, and network packets for further analysis. First, CPU usage is an important indicator of the execution of complex computations. For example, new types of cyber attacks, such as cryptocurrency mining and ransomware, can be identified based on the CPU usage. The process list can be also used to track unintentional threats. Deployment overview of our honeypot system, including Alibaba Cloud, Amazon Linode, Tencent Cloud, Google Cloud Platform. And here is a geo distribution of Europe, America, and Oceania. We deploy and the average cost of each. And now let's take a look at the findings. The first thing I want to talk about is the general attacking flow. For malware-based attacks, there are generally three steps to go through. First, intrusion. Second, infection. And third, monetization. In the intrusion phase, most malware uses brute force method to log in. After the attackers successfully log in, they enter the infection phase and download the required malware. The downloaded malware usually connects to the command and control server, we also call it CC server, to wait for the command. Once they receive the command, the malware can perform various kinds of attacks, such as denial of service attack, telnet or SSH scans. As for fileless attacks, which we'll define later, the attack behaviors differ from those for malware-based attacks in the second and the third phase. In the infection phase, no malware is downloaded. Therefore, traditional detection techniques based on malware fingerprinting cannot be applied. Instead, attackers modify certain system-level files or set up port forwarding and backdoors for later use. In the monetization phase, apart from the DOS and telnet SSH scans, we also discover a new behavior, which I'll talk it later. So how do we define a fileless attack? We define fileless attacks as attacks that do not rely on malware files. During the whole year, our hardware honeypots received 14.5 million suspicious connections in total. Among these connections, 85.8% are SSH or telnet connections, 6.2% are SMB, 2.5% are HTTP and HTTPS. And these connections led about 1.6 million effective attacks. 46.9% of them are malware-based attacks and 5% are Fileless attacks. As for the software honeypots, we had observed 249 million suspicious connections. Among them, 78.3% are SSH or Telnet connections, 8.9% are SMB, and 3.2% are HTTP and HTTPS. And these connections led about 26.4 million effective attacks. 55.3% are malware-based attacks, and 5.3% are Fileless attacks. The average attacks of hardware honeypot is about 1,100 per day per device, while the average attacks of software honeypot is about 670 per day per node. So what happened? We think the reasons are mainly twofold. First, some public cloud providers are likely to prevent certain types of attacks. And second, even if an attack reaches our honeypot, it is still possible that some attackers leverage more in-depth information and advanced techniques to infer the honeypot. The attacks against our hardware honeypots are categorized in this figure. The malware can be classified into 7 types, and most of them are Mirai. The typical behaviors are various kinds of flooding. As for non-malware, we generally group different types into two categories, with or without the file system changes. And the different types will be introduced later. Then the results of software version. To show the differences clearly, we mark the newly discoveries in blue. Again, Mirai takes a significant portion. We also found a new type of Fileless attack where no command happens. In total, we have collected 598 different types of malware. We also found that malware is usually targeted at different architectures. For example, 27.3% of them can run on ARM platforms, and 25.7% of them can run on MIPS platforms. And based on the behaviors and potential intents, we now group Fileless attacks into 8 different types. 1, occupying end systems. For example, the attackers may alter passwords. 2, damaging system data. They may remove or alter configurations. 3, preventing monitoring. For example, they may kill services. 4, retrieving system info. The attackers may get hardware information. 5, stealing data. The attackers may read the shadow file for further cracking. And 6, launching network attacks. The attackers may send malformed HTTP requests. And type 7, other commands. These are the commands that we cannot classify. For example, they may use the command who last log. We do not know why they just issue this. And type 8, there are no shell commands at all. For example, they may launch SSH tunneling attacks. This figure illustrates how we identify the last type, the most special attack. We call it SSH tunneling attack. First, by examining the recorded data flow traffic, we found that the outbound network traffic in one of our deployed software honeypots suddenly exceeded a reasonable limit. Then we found that it continuously sent HTTPS requests to a Bitcoin lottery website, freebitco.in. Then we searched the domain name of the website together with a keyword attack via Google. And fortunately, we discovered a message posted on Twitter by the website's operators, reporting that they're under DDoS attacks on the same day. Based on the findings, we're able to identify both new security challenges introduced by Fileless attacks and new defense solution directions. First, 56.2% of Fileless attacks modify the file system of the compromised IoT devices. Second, we find that 99.7% of Fileless attacks are using shell commands, making these attacks detectable by auditing the shell command history. Third, we note that there are 0.3% of Fileless attacks neither modify the file system nor do they execute any shell commands. As for defense directions, we provide this guideline to manufacturers to increase the security of their devices. First, they should make passwords as strong as possible because weak password is a major way to break in. Second, they should put as many files as possible in read-only file system to prevent the unintentional file system change. And third, they should remove useless components to prevent abusing system tools. Now, let's get the conclusions. First, we build and deploy the HoneyCloud system, and then we provide the first taxonomy for Fileless IoT attacks. As for the future works, we have three things to do. First, support of emerging IoT interfaces. Although Cameo provides emulations for a wide variety of peripherals, it still does not support some new interfaces like MIPI CSI, which is typically utilized by today's IoT cameras. Cameo also lacks the support of communications interfaces like ZigBee or NFC, which are commonly seen in home automation devices. This restricts our capability to design and deploy more kinds of IoT software honeypots. Second, robustness to the inference of identity. And third, in-depth analysis on advanced attacks. HoneyCloud currently cannot decrypt the traffic delivered in the SSH channel, so we do not know what exactly happened during the attack. So we would like to do something to solve the problem. That's all. Thank you very much.